So hello everyone, welcome to this first lecture of module 9, which is going to be on hardware security primitives. So in this module, we'll be discussing about physical unclonable functions and random number generators, which are most common hardware security primitives that are used in modern day. So before getting into the field of hardware security primitives, let us first understand why do we need hardware security primitives? What is their application or why do we need them? So needless to say, we are living in an era of Internet of Things, where we have all the smart devices, smart watches, wireless IoT nodes, and everything connected together. And each of these devices is in turn connected to the internet as well, which has been shown here in the form of cloud. So although these interconnected systems in this era of Internet of Things have made our lives more convenient than ever before, each of these IoT device is a source of security threat. So all these IoT devices connected to the internet, they form a part of the cyber physical system. So each of these devices, such as your home appliances, smart home appliances, your mobile phones and all, they are also known as cyber physical systems since they are connected to the internet. And each of these devices, since they are connected to each other, each of them could be a potential source of threat or adversary attack. So what exactly is adversary attacks? What are those threats? I'll discuss them just now. So what are those potential threats or security vulnerabilities? So some of them are unauthorized access. I mean, this is more commonly known as hacking. So people can hack into your mobile phones if you click on any malicious link or something. So that is one form of attack. Then there's this data identity theft. So unknowingly or knowingly, even Facebook, Amazon, or Google has been, tampering with your data. They have been stealing your data from your mobile phone. Although it was exposed recently, but they have been doing it for a long time now. Then the third kind of attack or the third kind of security vulnerability is this electronic counterfeiting, which we as electronics or electrical engineers are more interested in. So what this electronic counterfeiting means is that you replace the original hardware or the original components of any system with any fake component. So this kind of electronic counterfeiting is pretty common in China, where what they do is they kind of get involved in the supply chain. So suppose let us take the case of HP. So HP printer. So HP was the first company which came to us asking for a help regarding the security vulnerability, which was mainly electronic counterfeiting and reverse engineering. So what happened with HP was that all these printers are fitted with cartridges. So when these printers were exported via China, so what used to happen was in the supply chain there was some kind of a problem that people would take these new printers which were kind of manufactured by HP, they would replace its original cartridge with the fake cartridge. So the kind of printers that would reach the customers, they would have cartridges which were fake ones, and as such they did not last very long. So HP started receiving too many complaints and when regarding cartridges, and when they analyzed this the entire supply chain, they found that all those printers which were actually passing through China, they were having these problems. So when they looked at it, they found that all those printers had some fake cartridges. So what these companies may do in the supply chain, they kind of they can replace your original components with the fake components, and that is called electronic counterfeiting. Then another problem which is mainly in China is reverse engineering. So there are many companies in China. What they do is they kind of take these chips, then they etch it, lap it layer by layer, and try to image it, try to make a 3D map of the circuit. So once they etch it layer by layer, they're at the same time also imaging it from all the 3 or 4 sides, so that they kind of come up with the exact circuit that is there. And each of these circuit is unique to that IC, or each of these companies. For instance, let's say some company has come up with a voltage regulator IC or a ADC. So that ADC component is kind of a intellectual property, or I would say it's a unique component of that company. Each of the companies have their own unique IPs or unique ADC circuits. So these companies in China, what they do, they lab that chip layer by layer, they 3D image it, and then they find out, okay, these are the dimensions of the transistors, these are how the transistors are connected, and then they reverse engineer it. By reverse engineering, what I mean is they try to fabricate the same thing utilizing their own indigenous technology. So this way, they kind of get access to the circuits which these companies spend around 2 years, 3 years in design. So that is what is known as reverse engineering. So to remove reverse engineering, nowadays what people are doing, they are doing something which is called circuit camouflaging. So what they do is they kind of insert some dummy transistors, they kind of insert some dummy interconnects, which are not actually doing anything, which are not providing any meaningful circuit operation, but they're just to make these attackers fool. So they just put some dummy transistors, dummy interconnects, dummy oxide layers, dummy deposited layers, dummy caps, and those dummy layers are just to make these people fool. Okay. Then other form of attack is called side channel attack. So I'll discuss more about side channel attack in the next slide. Then I already talked about this intellectual property piracy. So all these ICs with several specs, the industries put a lot of effort in it. 2 years, 3 years, one team or two team designs according to the spec of the consumer. And these companies, within a matter of months, they kind of reverse engineer it, and then they sell it for then they sell it at a very cheap price. And this is one of the major reason why you get all the features of your best Apple or Samsung mobile phones in these mobile phones which come from China at a very cheap price. That is because all these features they try to mimic using this reverse engineering. So there are dedicated companies doing this in China. I should not be blaming a country for that. Even in India, these things are being done. But yeah, China is the hub of all these things, all this malicious behavior. So what is the best way to protect these systems, these IoT systems against these security threats? So all these systems have some kind of functional circuit, right? So if you can embed a security module in the functional circuit of each of these devices, that would be the best thing. And since CMOS and memories, especially NAND flash and all those things are embedded in all these devices for storage or even for performing some embedded system application, transistors would be there. So since transistors or CMOS circuits and memories are present in all these systems, it makes a lot of sense to use them as hardware roots of trust or as hardware security primitives. So what exactly are hardware security primitives? So hardware security primitives are nothing but they rely on the inherent variations in the CMOS circuit, such as RTN is there, noise is there. Then there's this stochastic behavior that your emerging non-volatile especially show too much. Even your NAND flash memories, you remember that the programming mechanism itself is very stochastic, and the kind of threshold voltage distribution that you see from device to device, that is very high. I mean, the distribution is very broad. So that way, these hardware security primitives rely on that kind of a variation. And each of those devices, for instance, let's say one CMOS circuit in this device, other CMOS circuit in this device, even if those are made identical on the same wafer, then they will have different properties, right? So if you characterize those circuit properties at the manufacturing level itself, and then embed them in these two different devices, and then if you send, let's say, the same voltage in both the devices and find out the typical response that you got during manufacturing, then you can check whether the devices or the devices that the consumer has received, they are the same devices that you manufactured on. That is the main concept behind the use of these hardware security modules. They can be used for identification, which I talked just now. They can also be used for cryptography, cryptanalysis, and making I would say secured communication over unsecured channels. For instance, your internet channel is something which is very unsecured. Anyone can tap into your channel and see what information you are sending. So all the information that you send from your mobile or your laptops, they're kind of encrypted. And for that encryption, you have a TRNG or true random number generator in your mobile phones as well as in your computers. So these hardware security primitives enable you to do that cryptography. They also enable you to decipher that encrypted information. So there are two major uses. First is cryptography, and second is this identification and authentication. So the kind of hardware security primitive that is being used for identification and authentication, that is called physical unclonable function. And the hardware security primitive that is usually used for cryptanalysis or cryptographic kind of things, or in decipher systems, that is basically known as your random number generator. So there is inherent difference between the two. Physical unclonable function has to have some kind of correlation with the device. For instance, the chip which is going here and the chip which is going here, although they are made on the same wafer, but they show different characteristics, and that characteristics is related to the transistors there or the components there. However, these random number generators, their characteristics should not be correlated with anything. So their kind of response should be uncorrelated with the underlying chip. So noise is the best form of producing any random number. So we'll see how we can use noise or even fluctuations and all those things for generating random numbers, or other different kind of behavior device to device variations which can be used for physical unclonable function. And I'll cite these. What I'll do is I'll try to explain these by giving two examples. So a PUF using 3D NAND flash and a TRNG using RM devices. But first of all, let us analyze what exactly is a PUF. So don't get overwhelmed with this figure. It will become clear as I discuss it along the way. So a PUF basically relies on challenge response pairs. So it kind of relies on the inherent device to device variation, as I already explained. And it exploits that inherent device to device variation in physical systems. And then a PUF, when excited with a unique challenge, gives you a unique response. And these unique challenge response pairs form the basis for identification. For instance, here I told that, let's say these two circuits, although if they are made on the same chip, if you apply one voltage to this and same voltage to this, the kind of response would be different, slightly different. So that kind of slight difference in the response, that forms the basis for identification. So that is what a PUF is, that is what PUF relies on. So it relies on that inherent randomness between devices. And then when you poke it with a particular challenge, you get a particular response. And that challenge response pair, which is also known as CRP, forms the basis for data identification and authentication. So each PUF instance, when you excite with a particular challenge, it should give you a unique response. And if you have different PUF instances, then if you apply the same challenge, it should give you different response. So that is how it works. So how basically PUFs are used for authentication is, so at the server end, or I would say at the manufacturer's end, suppose I manufactured something, some kind of printers or something. What I will do is I will kind of make different PUFs and embed in all the printer units. So each of the printer units will have a unique PUF. And then for each of these PUFs, what I'll do is I'll kind of use a challenge, and then I'll check the response of that PUF and then record it in my internal server during manufacturing itself, or just after manufacturing, before sending it to the client side or the consumer side. And once I send it to the client side or the consumer side, what I'll do is I'll ask, or I'll send this challenge, or the manufacturer will send this challenge over an untrusted channel to this PUF. And then the response which it gets, it will just copy or compare it with the response that it already has. So it just compares the response immediately after the manufacturing process, and once the product has reached the consumer end. And if they are matching, it confirms that, okay, the product that I manufactured, only that has reached the consumer. If not, then it will definitely say that, okay, your product is faulty or your product has been counterfeited, and we won't take warranty. So I won't give warranty on your product. So nowadays it has become a common norm to register your products over the internet. So while registering, what you're doing is you're essentially providing the response. So that response bit is being sent to that company's database. It just compares it with the original response that they embedded on your product. And if they're matching, then they tell that, okay, your product is something which is genuine, which we send to you. And since it is genuine, we'll provide you warranty, or we'll provide you additional warranty of 2 years or something. So that is the role of that pre-registration and all. That is what happens exactly in that process. However, what I was talking about in the last slide was this side channel attack. So I told that this is sent over the internet, and the internet can be accessed by anyone. I mean, there are a lot of hackers nowadays, and the number of hacking events has also increased significantly over the past 10 years or something. So there can be an attacker which can sense whatever is being sent over these channels. So he can sense the challenge bits that are being sent and the response bits which are coming out of the PU. So he can also prepare a challenge response pair, but that is something which is corresponding to the PUF which you are actually probing via this internet. So the attacker can get access to the raw CRP bits. He can get access to the raw challenge which is being transmitted over the internet, and the raw response bit which are being transmitted over the internet as well, over the other channel. What we can do, we can actually embed TRNG at both the ends, so that this information is also not the raw challenge pair, but it's actually an encrypted version of the challenge. So the encrypted, if there is a TRNG at the server end, An encrypted form of this challenge will flow through this channel, and then it will get decrypted here. Then the response will also be encrypted by TRNG, which is local to this unit. And then what the attacker will get is an encrypted version of the challenge response pairs, which doesn't contain any information about the real challenge and response bits. So encrypted data doesn't contain, I would say, only the decryptor can encode info, only the decryptor can assess that information or access that information, or find out meaningful things from that information. Apart from that, even if the attacker has those encrypted challenge response pairs, he cannot do anything. But if he has those raw challenge response pairs, so what he can do is he can use something which is called a machine learning modeling attack. So these challenge response pairs, which he probes through the side channel attack, this can act as a training set for his neural network. And then if the server sends an unknown challenge, he can send that unknown challenge as a what should I say, a test data to his, he can present that unknown challenge as the test data to his neural network, and then he'll get a response based on whatever training data that he has given to his network. He'll get a response, and that response can be very close to this response which the PUF is generating, if the PUF is not very complex, if it's a linear PUF like a CMOS PUF. So I'll discuss about that later. So this kind of machine learning modeling attack can also be performed on a PUF, and that is why these side channel attacks are really dangerous. So given the raw challenge and response pairs, they can kind of find out, the response bit which an unknown challenge can generate with the same PUF. So that way they'll be able to hack into the system. So that is why this is kind of dangerous. So there are two kinds of PUF. So the first PUF is a strong PUF where the number of challenge response pairs is huge. So if you have a huge number of challenge response pairs, let's say 10 per 20 or 10 per 30, then it becomes really impossible for the attacker to characterize all these challenge response pairs using economically and in a I would say small interval of time, or in a small kind of time frame, because time frame is also which is very important. If for encrypting or decoding the response bits of one PUF, it takes him like 1 year or 2 years, then after 1 year or 2 years, the technology itself changes. So the PUF will change after the technology, which is like, so the PUF which is embedded in the products which are coming after 1 year, till the time his machine learning model gets trained, will change. And as such, he'll have to again probe it, and the time again will be like, let's say one year or 6 months or 8 months. So if he cannot kind of access, or if he cannot kind of model that data, the challenge response pairs well, if there are a huge number of challenge response pairs, then it would be really difficult for him to prepare a good model for it in a limited amount of time with limited amount of resources, such as computational resources, in an economical way. If the cost of cracking this PUF itself is too high for him, why would he go for that? Especially if it takes like around 6 months to 1 year, and he knows that the technology would change, the PUFs that are going to come in, the new technology would change, then there's no point going for that. So that is why the strong PUF should have a large CRP set, and it is generally used for data, it is generally used for device authentication. There's another set of PUF which is called a weak PUF, where the number of CRP set is limited. So if the CRP is limited, your network can actually learn these limited CRPs, and then it can effectively predict any response given an unknown challenge. So this is not used for authentication purpose, because it would be susceptible to machine learning modeling attacks. And this is generally used for cryptographic key generation. So key generation is like OTP. You generate a random number, you generate a key, and then you just verify whether that key was transmitted correctly or not. So that is what is the use of this weak PUF. So now with this, let us discuss about the different sources of variability in emerging non-volatile memories, with a special focus on RRAMs and STT-MRAMs, and also discuss about PCM and all those devices here. So the first source of variability that I'll be talking about is the cycle-to-cycle variability, or the cycle-to-cycle stochastic behavior. So I had been referring to this as temporal variability in the lectures. So what are the different reasons for it? So the reasons can be intrinsic physics. So for instance, in RRAMs, as I told that, the conductive filament formation and dissolution is a stochastic process. And that is kind of coming from the physics, right? So because of that, the intrinsic physics leads to kind of a cycle-to-cycle or temporal variability in RRAMs. So what I told that even if you apply same voltage for set and reset for different devices, or even for the same device, if you apply the same voltage in different cycles, then your HRS resistance or the LRS resistance won't be same. Why so? Because every time you are dissolving that filament or creating that filament, since it's a stochastic process, the extent to which the filament diameter will increase or the filament length will decrease, that is completely stochastic. So you'll have some kind of fluctuation, some kind of, I would say, variation, and that is coming because of this intrinsic physics. So that is one of the reasons of this cycle to cycle or temporal variability in RMs. Similarly, there are other reasons in other devices. Then there can be this weak programming condition. So weak programming condition, what do I mean by that? So by weak programming condition, what I mean is you don't apply extreme voltages, you apply voltages which show a probability of switching which is 50%. So in case of RRAMs, let's just take, for instance, the case of RRAM. We don't apply extreme set threshold voltage or the extreme reset threshold voltage, but suppose we want to change from HRS to LRS. Along the way, statistically, we find out a particular value of voltage which would be lower than the set threshold voltage, extreme set threshold voltage, for which the device switching probability will be 50%. And then we apply that voltage. So every time we apply that voltage and we are in LRS, we are in HRS, we never know, or the probability that the device will switch will be 50%. So in that case, that can be used for random number generation. So that is for another problem or one other kind of source. And then there can be these thermal fluctuations. These thermal fluctuations are especially important for STT-MRAM device. So I discussed somewhat about STT-MRAM devices in this slide itself, because I won't be covering it in this course. So what are these? So where are these where do you observe these things? So you observe these in OXRAM devices, STT-MRAM devices, CB-RAMs. You also observe this in PCM devices, and 3D NAND you already know. Then in 3D NAND also, if you apply weak pulses, then you won't achieve extreme threshold voltages. So the probability of you'll have some probability. So you see these things. I mean, you see this temporal variations and all those things in all the devices. In 3D NAND flash actually, or NAND flash memory, it's the oxide traps and all these things also add to this. So there the situation is much more complicated. And what are the implications? So you have this switching probability, as I told, that you can achieve a switching probability of 50%. Then you have cycle to cycle distribution of your threshold voltage. So in each cycle, your threshold voltage at which the device switches from HRS to LRS will change. And as such, you'll have a distribution of VSET, VRESET, that's the threshold voltage, the threshold current values. Then if you're talking or if you're programming your device with the help of, constant pulses, then the time of set or the time to reset, that will also have a distribution. Then the LRS and HRS resistance will also fluctuate from device to device, not from device to device, from cycle to cycle. So directly, what can this be used for? It can be used for RNG. And indirectly, if you couple it with device to device variation, then you can also use it for physical unclonable function. Now, let me just give you a brief overview of STT-MRAM, or how exactly the cycle to cycle variations occur in STT-MRAM, what exactly is STT-MRAM, how it operates, and all those things. So in STT-MRAMs, what you have is, it's also a 3-layered structure. You have a ferromagnetic material, which is called free layer. So you can tune the polarization, not the polarization. We are talking about magnetism. So you can tune the moment of this free layer with the help of charge current or spin current. How? That I'll discuss later. So it's also kind of a 3-layered structure. You have a ferromagnetic material here, who's kind of, so in this diagram, actually, I've shown this as the pinned layer and this as the free layer, because you see, I've changed the configuration of this moment of this. So let me discuss like that only. So in STT-MRAMs or any magnetic RAM, you'll have 3 layers. So there would be 2 ferromagnetic layers. One of them would have a pinned, one of them would be a pinned layer, or the magnetic moment of that layer cannot be switched, which in this case is this one. So its magnetic moment cannot be switched. However, one of them would be free layer, whose magnetic moment or magnetization can be switched. So if it is in this direction, by passing a spin polarized current through this layer, or by applying a spin orbit torque or spin transfer torque, you can change its orientation in the opposite direction. So if the orientation or the magnetic moment of both the ferromagnetic layers is same, it is called the parallel state. And if the moment of these two ferromagnetic layers are in the opposite direction, that is called anti-parallel state. And what is in the middle? So in middle, you have a tunneling layer through which currents or electrons can flow. So how you switch it? So suppose you are in this configuration that is anti-parallel. So what you do is you pass a current through this layer. So as the current passes through this layer, this pinned ferromagnetic layer, what exactly happens is it's the property of these kind of ferromagnetic materials that they try to align the magnetic moment of the electrons which are flowing through them along their own direction, along their own spin direction or along their own magnetic moments. So I am using spin and magnetic moments, I would say reversibly here. I mean, I am using spin for magnetic moment and so on. So let me just also give you a brief overview of how spin comes into picture for an electron. So you must have heard about, what was that theory which says that, not two electrons cannot have same, all the four quantum numbers as same. So that gives rise to this concept of spin, half spin up or half spin down. But, to explain this, I would say in a very layman way, what I would do is I would ask you to imagine the case of an electron revolving around the nucleus. So if the electron is revolving in clockwise direction, so motion of electron constitutes a current, right? So if the electron is revolving in the clockwise direction, your current is actually flowing in the anti-clockwise direction. And you may know Biot-Savart's law from class 12th. So what Biot-Savart's law says that if you roll your fingers in the direction of the current, then your direction of the thumb will give you the magnetic field. So if your current is flowing in the anti-clockwise direction, you roll your fingers, you curl your fingers in that direction, and your thumb direction will give you the direction of magnetic moment. So that is how, these magnetic moments are coming into picture. So some of these electrons revolve in, clockwise direction, some of them revolve in anti-clockwise direction. And that leads to two different kind of magnetic moments of electrons. Now, this layer has, let's say, electrons polarized, or I would say electrons having spins or moments in one direction, let's say in this direction, which is pointed out by the arrow. Now, if electrons are flowing, like charge current is flowing through this, what that means is electrons are flowing through this layer. Now, when electrons flow through this layer, in ferromagnetic layer, you have a property which is called spin transfer torque. So what exactly happens is, because the spin of those electrons which are coming into this layer is randomly distributed, and the spin of the electrons in this, or the magnetic moment of the electrons in this layer, is kind of fixed in this direction. Because of the difference in the spin orientations, these electrons which are coming out, or these electrons which are coming because of that current, they suffer, or they kind of undergo a torque. They experience a torque which tries to align their spin along the direction of this spin layer. So the electrons, the charged electrons which are coming from the battery, they enter this ferromagnetic layer. Here they experience a spin transfer torque. That torque tries to align their spin along the direction of this spin layer. And then through this tunnel layer, they flow into this layer. And once those electrons flow into this layer, since the number of electrons that are flowing into this layer are huge, those electrons tend to, and since this is not a pinned layer, but this is a free layer, what those electrons do, those electrons are polarized in this direction, or those electrons, I would say, having magnetic moments in this direction. So once they reach this free layer, those electrons exert and spin orbit torque, sorry, not spin orbit torque, that's an entirely different concept. Those electrons exert a spin transfer torque on this free layer, the electrons present in this free layer, and they tend to, rotate this, I would say, effective polarization or effective moment of this free layer from this direction to this direction. So they tend to reverse it just by applying that torque. I mean, the charge current which flows through this spin layer, that gets spin polarized, because now the electrons will have their polarization or magnetic moments in the direction parallel to this spin layer. Now those electrons, those spin polarized electrons, they enter into this free layer, and the moment they enter into this free layer, they again start exerting torque on the electrons which are present in this free layer, and they switch their magnetic moments in the opposite direction. So from here, you attain this. However, the problem with STTM ramps is that, the kind of switching currents required for reorienting or making this from anti-parallel to parallel state is huge. The current densities are huge. That is one problem which is present with STTM RAM devices. Also, how you sense the change in this configuration from parallel to anti-parallel and so on. So in parallel configuration, if you probe its resistance, so its resistance is low, as compared to your anti-parallel state. So when your device is in this state, you have a resistance which is higher, and when your device is in this state, you have a resistance which is low. And what is the resistance that I'm talking about? I'm talking about the resistance between these two terminals. If you have electrode here, if you have electrode here, then the resistance which is shown by these between these two electrodes, that is lower for the parallel case and that is higher for the anti-parallel case. And the difference between the RAP minus RP divided by RP, that is called TMR, or magnetoresistance ratio. So STT MRAMs show a magnetoresistive ratio of magnetoresistance ratio of like the maximum ratio that they have shown is close to 8. So the RAP and RP, they are not much different, and the range of resistances that these STT MRAM devices show, that is close to some kilo ohms. So that is also one factor which kind of did not enable their prominent use, but they are very fast. That's one kind of advantage, that they are very fast. So people are actually thinking of replacing your cache memory with these memories. Okay, and so if you look at their energy kind of landscape, you see that you have these two states. You have these two stable states. One corresponds to your parallel state, one corresponds to your anti-parallel state. So how basically people utilize them for these hardware security primitives is that if you excite these, I mean if you provide an energy such that from here or from here, I mean starting from any of these states, it kind of gains an energy and reaches this plateau or this peak. So if it reaches this peak, there's an equal probability that it can even go this way or that way, depending upon the thermal fluctuations, right? So if the system is in this state, if the electrons are in this state, and then, so which electrons could be in this state? The electrons in the free layer. Because pinned layer is fixed, you cannot change its kind of momentum, magnetic moment, not momentum, magnetic moment. But you can change the magnetic moment of this free layer. So if you can somehow excite this free layer electrons to reach this state, then depending upon thermal fluctuations or the energy gained via thermal collisions, they can reach even this state or that state. So this is highly probabilistic. So that is how you can achieve a probabilistic switching in your STT-MRAM, and that you can use for RNG, which is the kind of general use. So that is something about this STT-MRAM. There's also this read, write, and retention trilemma in STT-MRAMs. This barrier which I showed here, it's actually very low. So if you want to have these states separated by a huge energy barrier, I mean for retention, what you want is these barriers should be huge, right? So that even if the thermal fluctuation is large, the state of the device doesn't change, or the device doesn't go from this state to this state. If this barrier is large, even if the thermal fluctuations are small, even if the thermal, so if this barrier is large, even if the thermal fluctuations are large, you can ensure that device won't grow from here to here just because of the thermal fluctuations. However, if this barrier is large, you require a huge amount of energy to write this device, or a huge amount of energy to change your state from this to this. That is your write retention dilemma. And there's also this read write kind of a dilemma, which you can actually read from the review paper that I'll share in the resources. I don't want to get into the details, but there is this trilemma which is there in this STT-MRAMs, which still needs a solution. Anyway, so I discussed a lot about these STT-MRAMs. I mean, not a lot, but I guess now you will be able to understand or appreciate wherever you read about STT-MRAMs. That was more or less, kind of enough information for you to understand or comprehend STT-MRAM. Now let us come back to the main topic of discussion, that was different sources of variations. So what are the other sources of variation in the emerging non-volatile memories? So you have these transients. You have variation in these transients. So transients, I mean pulses. It can be switching pulse. It can be a read pulse also. So also the reason for this is again the intrinsic physics or the thermal fluctuations. So noise, what is the main reason? Thermal noise is thermal fluctuation, and apart from that, your short noise and all those noises, they come because of inherent physics, right? So that is what is the reason behind the noise. It's mostly noise, and also there is some kind of a fluctuation, or there's some kind of a transient current fluctuation during switching of these OXRAM devices. Why so? Because I told that there is this tunneling phenomena which may happen between the conductive filament and the virtual electrode. I mean the virtual electrode and the bottom electrode. And since the tunneling phenomena is very sensitive to the distance or the tunneling gap, so you can have these current fluctuation, reset transients. So that is what I basically mean by this reset transient. Apart from that, you can have read fluctuation. So during read also, what you are essentially doing is you are supplying some energy to the device. And because of that energy, if your read voltage is somewhat higher, let's say 0.3 or 0.4 volts, then what it may lead to is it may lead to a change in the conductive filament configuration. So it will fluctuate. It will fluctuate around some value. So that is also something which leads to some kind of variability. There's also this 1 by f beta noise. 1 by f beta noise is nothing but flicker noise, a form of flicker noise, and which you can also relate to RTM. So this random telegraph noise, this 1 by f beta noise are kind of same kind of noise. They can also be pink noise. They can also be even your what is that noise called? I'm just forgetting the name. Anyways, so it can also be because of short noise. Yeah. So short noise in 3D NAND flash or NAND flash memory, that is the major cause, because short noise is very prominent in the sub-threshold mode of operation. And usually you kind of operate in sub-threshold mode when you talk about 3D NAND flash or NAND flash. Why? Because you are more interested in the threshold voltages. So the current or regions around threshold voltage is sub-threshold mode. So there, these short noise is very dominant. And what these noise can be used for? This can be used for definitely two random number generators pi, because noise and all doesn't have any correlation with the device under consideration. So it can be used for RNG. What can be other sources? So we have so far discussed about noise, which is transient. We have so far discussed about cycle to cycle or temporal variability. What we're missing on? We are missing on the device to device or the spatial variability. So let us talk about device to device variability. So as I told, because of process variations, we can have like different devices on the same wafer showing different threshold voltages, different resistances, although they have been manufactured using the same process. And it is generally unintentional. But when we are going ahead and making PUFs or making, RNGs, it can be intentional. We can actually, tweak our fabrication process so that we get some more amount of variation as compared to the general process. We can tweak it. See, always it's easier to get more variations than to make a uniform kind of process. So intentionally, we can also induce some amount of variations. And it has been reported in OXRAM, STT-MRAM, all those memory devices that we have studied so far in this course. So what are the different sources of variability? So there can be a device to device variation in the thickness, uniformity, interfaces, geometry, and all this lead to a change in VSET, I reset, T set, and R on by R for all these devices along the chip. So thickness because of deposition process, uniformity because of the your lithography, interfaces because of your PR. I mean, the photoresists also do not etch very perfectly. So because of that, the interfaces are generally rough, and that is why you need to go for CMP process. Then geometry also is something which affects it. So geometry, especially in these STT-MRAMs, you use a cylindrical kind of geometry. If you go ahead and use some other geometry, like rectangular or something, your magnetic moments won't be aligned in this direction. So all the magnetic moments cannot be aligned in this direction. Cylindrical kind of geometry with this thickness, very small as compared to the height. So this this height or this thickness is very small as compared to this dimension along this. So because of this, because there is a phenomena which is called surface anisotropy, the magnetic moments get aligned in this direction. If your height would have been higher and if the height would have been higher and this dimension would have been smaller, then most of the magnetic moments would align along this direction, in the upward direction. Why? So because there is something which is called surface anisotropy in this spin dynamics. I mean, I'm not getting into the physics of this because it has got a very rich physics, and even one semester is small to explain all those phenomena, starting from Linux Pauling concept and going ahead with ferrimagnetism, polymagnetism, all those things. I mean, it would require at least one semester to go about telling you all those concepts that are involved in spintronics, and then go ahead and explain this STT-MRAM to you. Anyways, let us forget about that. Let us come back to the device to device process variations. So where we can use it, we can directly use it for PUF, as I told you, and then we can also use it as a seed for RNG. Why seed? Because in general, your random number generators that is present in your mobile phones or your laptops, they are pseudo random number generators. So they are basically using LFSR, the shift registers. So those shift registers are actually large shift registers. So till 1 million cycle, they'll tend to produce random numbers. But after 1 million cycles, they'll start again producing the same set of numbers, the same sequence of numbers. So at the end of 1 million cycle, what you need to do is you need to give it another seed, which is called a random seed. And depending upon that seed, the state of that LFSR changes. And then it produces again, a set of new 1 million numbers, which cannot be, recognized if you know the previous 1 million digits which are coming out of your RNG. So that is how you, that is why you need this seed and all. Anyway, so let us go ahead and let us talk about this 3D NAND flash in some detail. And then by example, I would tell you how a PUF works and how we can design a PUF basically. So I'll take the example of a 3D NAND flash. So you know that it requires a punch and plug process. You etch holes in a stacked metal and insulator. I mean, these are stacks of metal and insulators. Then you etched a hole. Then you deposit this ONO layer and this polysilicon, then a core dielectric, and you made a macaroni body kind of a 3D NAND flash memory. So I discussed already that it has got ultra high density. It is having a multi-bit capability. QLC is already there. 4 bits per cell is already there. Industries are already at 192 layers. However, I also discussed that they have rarely been used for system or circuit level applications. Reason being, there was no compact model until recently when I formulated a compact model for it, through which you can use it for some meaningful application, through which you can realize some meaningful circuits or systems for using 3D NAND flash memories. So that is what I told, that there's no methodology to extract system or circuit level performance estimates. And what is the best kind of a methodology? You formulate a compact model and use that compact model to generate or design some circuits or some system level applications and then use it. Also, given the wide range of application, I mean, if you look at this 3D NAND flash memory, it's omnipresent, right? All the devices in the universe right now, all the smart devices in the universe, they have this 3D NAND flash memory or some level of flash memory embedded in them. So given their wide range of integration and application with all these cyber physical systems, all these IoT systems, it is kind of, it is obvious or it makes sense to, explore its potential for hardware security application, right? So that is what I did. So what I did was I first characterized the individual cell variability. So in your 3D NAND flash cell, what can be the sources of variations? So let's talk about it. So there can be process non-uniformity. So these are two different pillars along the string, not along the string. So these are two different strings basically along your 3D NAND flash array. So there can be a difference in the cell length. When you are fabricating this cell, their WL lengths can be different. Their widths can be different. Their oxide thickness can be different. I mean, ONO thickness can be different for each of these cells and different strings. There can be this random dopant fluctuation because your bit line and source line are heavily doped. So some amount of these dopants can encroach this WL0 or this WL9. And just to remove this random dopant fluctuation and also to achieve good programming, what they do is they also incorporate a dummy word line just close to this BL and close to this SL. I mean, close to this SSL and BSL, they have this dummy word lines, which are not used for memory application, but they are there to prevent this effect of random dopant fluctuation and programming variation, because close to this BSL, this word line will see a different kind of, so it will see one of its terminals as doped as compared to the other word lines. So that leads to a difference in the behavior of this kind of cell as compared to the other cells. So because of that, they insert a dummy cell. So there's this random dopant fluctuation. Then since you are using punch and plug process to etch high aspect ratio trenches, what you end up having is not a cylinder, but a kind of tapered cylinder, right? And also the taper angle will be different for different strings along the array. So that will also create some amount of variation. Also, because of the PR, so the PR are not etched perfectly. So you'll have some line edge roughness. So along these edges, you won't get a perfect cylinder, but you will have some roughness as well as you will get a taper cylinder kind of structure. So yeah, tapered pipes with different taper angle, as I already mentioned. Also, the channel is polysilicon. So once you have polysilicon channel, grain boundaries are inevitable, and their location and their size, they are different. So these all are grain boundaries. Whatever I have shown here, these are grain boundaries. So you can see that their sizes are different, their locations are different, their configuration is different, and also traps are bound to be there in between two grain boundaries, and their concentration and location in the energy landscape, that also has to be different for different strings along your array. So because of all these artifacts, polysilicon channel leads to huge amount of variability. Why this kind of variation is not very I would say, effective, or why it's not visible during digital memory application. This is because you have this error correction circuitry, which is huge part of this 3D NAND flash memory circuits. So because of this error correction circuitry, for memory application, it's perfectly fine. And also you saw that for third generation VNAND, they had different programming voltages for different layers of these 3D NAND flash. So they have all sorts of those mechanisms in the peripheral circuitry by which they counter the impact of these sources of variations. However, for hardware security, what we need is, we want these variations, right? We want to exploit these variations. So it would be a great idea to exploit these variations. So what I did is, first I formed a cell library for performing Monte Carlo simulations, considering all these variation sources in HSpace. Or actually, I made a cell library for 3D NAND flash string to characterize the variability in the string current because of all these sources. So utilizing that Monte Carlo simulation library that I created, what I did then was, I performed Monte Carlo simulation and I found this intrinsic string current characteristics for 10,000 strings. So what I mean by intrinsic string current characteristics, I am not programming it to any other level. It's in the same erase state. And then I'm just performing this Monte Carlo simulation. And in each instance, I'm having different values of these characteristics. And if I do that, the kind of characteristics that I get is shown over here. So this is the nominal characteristics, and these are by the cells, by the different cells, or by different strings along your array. So each of these characteristics corresponds to one string. You can see that not only the threshold voltage is changing because of those different sources of variation, but also the subthreshold swing is also changing. You can see that here the subthreshold swing is small, here the subthreshold swing is high. So even the subthreshold swing changes because of those sources of variation. And here I've shown it for two different word line address. So what word line address 00001 means is that 0 indicates that the cells are in pass mode or read mode, and 1 indicates that I am sweeping its word line voltage. Similarly here, I have swept the word line voltages of the first 5 cells, and I've kept the other bottom 5 cells in the pass mode or read mode. So one other observation that you can draw from here is that the moment you are probing more than one cell, the amount of variation is small. The moment you are probing only one cell in a string, the amount of variation is large. So these were the few observations that I got. So as I told, threshold voltage and subthreshold swing also changes. So the point that the subthreshold swing is also changing ensures that even if we shift its threshold voltage in this direction or that direction, we cannot mimic the other string characteristics. Why? Because apart from the threshold voltage, the subthreshold swing also needs to be same in order for two IDVG characteristics to remain same, right? So by partially programming, if the subthreshold voltage, subthreshold swing were same, then by partial programming, we could have shifted this curve, and then we could have reproduced the characteristics of the other string as well. However, since the subthreshold swing is also changing, we cannot reproduce this just by using partial programming. That is one advantage. Then, as I told, that variation is larger for string with only one active cell when we are probing only one cell. So that is another observation. So for different addresses, you have different distributions, distributions. And this is for one 3D NAND flash array. If you take two different 3D NAND flash array, you'll definitely get different distribution, even for the same word line address, because of the device to device variations. So this is actually very unique. No one had actually characterized this before this work. So this simply tells you that even if adversary has access to one 3D NAND flash memory and he characterizes, let's say, this word line address 00001, he finds out that this is the kind of IDVG behavior that we are getting. But if he gets another such POF instance, which is made on another 3D NAND flash array, that array will be significantly different than this. And even if he applies this 00001 there, he won't get this distribution. So whatever machine learning modeling attack that he wants to perform using this as the training set won't work on the other kind of string. So that is the advantage of this. Okay, so how can we design a 3D NAND PUF? So what I did was I kind of sampled the intrinsic string current for different strings at a particular word line voltage, let's say 0.8 volts. So what I did, I sampled at 0.8 volts, what is the value of string current of all these strings? And then I found out the differential string current. That is a difference in the string current between two different strings. And those two different strings can be located anywhere along the array. They can be either neighbors or they can be located far off. And when I plotted that differential string current, what I got was that it followed a Gaussian distribution, and the minimum difference between the two string currents was 6.3 nanoamps. So if we use a current sense amplifier, which has got a sensitivity of 5 nanoamps, then we can even manage to kind of compare the currents between all of these strings in that array. And if you look at this, when you are using when you are probing 5 different cells in this 3D NAND flash string, then you can see that the minimum differential string current reduces 2.6 nanoamps. So in this case, we'll have to get a current sense amplifier with a higher kind of sensitivity. Higher sensitivity, I mean a lower kind of precision, let's say 1 nanoamps or something. Since the string current is following a Gaussian distribution, one way to design a PUF is simply, take two different strings, compare their currents, and then generate a response bit. So what would be the challenge? The challenge would be first the row address, that is this word line address, how many cells we are probing, and that I can concatenate with the column decoder address. So column decoder address will simply give the column address of the two strings for which I am comparing the current. So the challenge would be what? The challenge would be row decoder address, which will give you the number of cells which I am probing, concatenated with the column address of the 2-bit strings. Let's say I'm taking bit line 1 and bit line 2 and comparing their currents. So the challenge would comprise of this row decoder address, which can be 00001, and then you add to it the column address of the first bit string and the column address of the second bit string. And then what you do is you kind of compare their currents and then generate a response bit. So this is how you can generate challenge response pairs. So this kind of simple PUF circuit includes one comparator and a row decoder and a column decoder, right? So as I told, bitline addresses of the two strings would be fed as is concatenated and fed at input challenge for same word line address, and then you get response bits. However, here, since the source line is common, you cannot do it in single cycle. So that is why I added a capacitor. So what we do is, first, in one cycle, what you do is, you first turn on this BL0, let's say. So you turn on this VBL0 first in the first cycle. You sample its current in this capacitor C1. So the current across this capacitor, the voltage across this capacitor changes and it reaches this value, which is VC1. In the second cycle, you disconnect this switch to the common source line. You connect this switch and then you select this BL1, sample its current on this C2. So you reach a particular value, which is VC2. And at the end of the second cycle, you just perform this comparator. You just enable this comparator, which will give you you sample the comparator's response. I mean, this comparator will always be on. It will give you some response, but you sample it only at the end of the second cycle. And by doing that, you will get some response bit. So this is how you can generate your challenge response pair using a simple 3D NAND flash array. And yeah, it takes 2 cycles. So that way it's slower. Anyways, flash is slower, so that doesn't matter much. So what are the other PUF designs that people generally use? So people generally use these architectures for PUF. So I thought that it would be good to sensitize you with these architectures. So the first one is called an arbiter kind of PUF. So this is called arbiter PUFs. So what here people do is they take 2 different paths, and these are muxes. So these muxes, what they do is basically they enable propagation of signals through them. So what essentially happens is the input is then distributed in 2 channels, and then it is sent to the final output with the help of these arbiters. And there is a rat condition. I mean, there's a rat race condition. So the signal, the path which produces or gives you the least delay, that wins this race condition, and that is different. Why that is different? Because you have employed these RRAMs, you are programming them using same condition. So their resistance are kind of close, but they are different. And you never know whether this I10 path or I20 path will provide you a lower resistance. So this way, they kind of propagate a signal through both of these paths, and the path which is having the kind of least resistance, that wins, and depending on that you receive an output. So here the race condition is basically responsible for this, and it's because of the variations in the RRAM that is giving you the variation in the path length or the path resistance. You can also achieve similar thing, I mean a similar kind of comparison based PUF using 1T1 array. So here you kind of provide the address of the rows and then address of the column. Then you kind of sense the current. So you can choose. So here the thing is, you can choose some of the rows, you can choose some of the columns, then integrate the current, which is called IA. Then again, in the second cycle, you can choose some of the rows, some of the columns, which are different than the first, and then you can kind of calculate the current, which would be IB. And then the sense amplifier just compares IA with IB, and then it generates a response. So this is also one way in which people have generated PUF using this 1T1R array. The second, or the most, I would say, simplest of architecture, similar to what I use. Here, what people do is they tend to program their RMs throughout the array with the same programming voltage. And you know that the kind of resistance value that they'll attain will be different. So then what they do is they kind of probe one cell, compare its resistance with the other cell, and that is how they generate PUF. They can also, generate this UF response by comparing this resistance with a fixed resistance. That is also something that people have already done. So these are few, kind of ideas that people have already used for designing PUFs, and they are very intuitive. I mean, these are very, I would say, preliminary or trivial kind of ideas. They're also very advanced kind of ideas where they kind of encrypt the challenges, they kind of encrypt the responses, and then, then you start enjoying it. So anyways, I won't be going into detail because the main aim of this course is just to sensitize you or just to educate you on how to design PUFs, how you can exploit variations to design PUFs, and what exactly are PUFs, what are the different performance metrics. So let us talk about the performance metrics of PUFs now. So the first and the most important performance metric, I wouldn't call it most important, but yeah, one of the important performance metric of any PUF is uniformity. So by uniformity, what do I mean? So I mean that the distribution of bits zeros and ones in the response bit stream. So you are applying challenges to the input of this PUF, you are getting responses. So as you are applying challenges, you are recording those responses. So the number of zeros and ones in that response stream, that has to be 50% of the total value of responses that you are calculating. So it is defined as this. I mean, the number of zeros or ones divided by the total number of bit response that you have calculated. So ideally, it should be close to 50%. I mean, the number of zeros and ones should be equal, and 50% of the total number of the bit stream, the number of bits in the bit stream. So what I did was I actually took these many response bits for the 3D NAND flash PUF, and then I grouped them into packets of 1000 bit each for this analysis. And then what I found out was I just calculated this thing: number of zeros or number of ones divided by the total number of uh, you know strings or number of bits in my bit stream. So these were the distribution for different word line address. So what I found that they show a kind of Gaussian distribution, and you have a mean which is close to 50, and there's a sigma or a variance. So since the mean is close to 50%, we would say that it shows close to ideal kind of uniformity. And we want this 50% uniformity for classifying any PUF to be ideal PUF. In the second parameter, and why this is necessary, because we don't want our PUF to be biased towards a 0 or towards a 1. Because the moment it gets biased, the attacker can do machine learning modeling attack, and there he would know that your PUF is biased towards 0 or 1. And then it would become easier for him to generate responses or to kind of predict responses of unknown challenges. So that is why we don't want it. Then the other parameter that PUFs should satisfy, or the criteria that PUFs should satisfy, is diffuseness. So what exactly is diffuseness? So diffuseness is the similarity in output response bits corresponding to different input challenges to the same PUF instance. So I have one PUF instance. At one point of time, I probed it with one challenge, I got a response. If I probe the same PUF with a different challenge, it should give me a different response. That is what I mean by diffuseness. And how is it calculated? So how can you assess whether two response streams are identical or they're different? So there's a parameter known as Hamming distance. So Hamming distance simply calculates the number of positions or the number of bits, number of positions where the bits are changed between two binary streams. So for a perfect diffuseness, what we should have is the diffuseness should also be 50%. What that means is, it means that half of the bit streams are changed. Half of what? Half of the total number of bit streams are changed between the two response bits. So Hamming distance basically tells you the number of places where your number of where your bit 0 has been replaced by 1, or your bit 1 has been replaced by 0. So if this is 50% of the total number of bit streams, then you can find that, okay, my response bit is completely different, is completely independent of your other response bit. So what I did was, to perform the simulation, I kept the I gave it a different word line address for bit strings, keeping the bit line address same. That is how I generated different challenges. And corresponding to different challenges, I also grouped in packets of 10,000 so that it was easy for analysis. And what I found out was that the fractional Hamming distance was close to 50%. When I had these two word line addresses, when I had other combination of word line addresses, and this simply means that it is perfectly, like, it is having independent responses to different challenges. My PUF is showing independent responses to different challenges. That is what it shows. Then there's another process or another metric which is called uniqueness. So what this uniqueness means is, suppose I have different PUF instances, I have different flash strings, I have different flash arrays, and now I apply same challenges to different flash arrays which are fabricated on the same wafer. So what I should get is, I should get different response bits. Just because they are different flash arrays, they are different PUF instances, even if I apply the same challenge to each of them, they should give me a different response. So this is characterized by uniqueness. So if there are two different PUF instances, when they're excited with same input challenge, they should give me different challenges. And the difference with diffuseness is you have one PUF instance, you are applying two different challenges. Here, you have two different PUFs and you are applying same challenges. So if you apply same challenge to different PUF instances, then you should get different responses. And how would you characterize whether the response bits are different? Again, you will use the same concept of fractional Hamming distance, and it should be close to 50% to ensure that these two are entirely uncorrelated. So even for here, we'll use this fractional Hamming distance, which is calculated using this formula. And what I did was, for generating different PUF instances, I used different random seed for Monte Carlo simulation. I won't get into the details, but this is how you can generate different PUF instances. And then I grouped them in packets of 1,000 bits so that my analysis was simpler. And then when I analyzed it, I found that even for different word line addresses, for different PUF instances, the response was kind of showing you a fractional Hamming distance of 50%. The mean was 50%, and it had a variance, which was also very small. So even this criterion of a good PUF was satisfied by the 3D NAND PUF. So the response packets corresponding to same challenges to different PUF instances are mutually exclusive. That is what it means. Another important parameter which characterizes PUF is the reliability. So what reliability means is, reliability simply means that if there is a PUF, you applied some challenge now. Now 10 years later, if you apply the same challenge, you should get the same response. The response should not change. Or for instance, if you have a PUF which is operating at, let's say, 10 volts, and then you're applying some challenge. If suddenly there is a spike fluctuation in the supply voltage and the voltage ranges to 15 volts, then also if you apply the same challenge, you should get the same response. Or let's say you designed your PUF to operate at, let's say, 25 degrees Celsius or 27 degrees Celsius, or at the room temperature. Suddenly you brought it in, suddenly the room caught fire and it is operating at 125 degrees Celsius. Even at that temperature, if you apply the same challenge, your PUF should give you the same response. So it is the reproducibility of the response bits over different measurement instances, that is your time, or different operating conditions, generally harsh operating conditions, such as supply voltage fluctuations or temperature fluctuations. So yeah, what I was telling, extreme temperature ranges or fluctuation in the supply voltage. And this is characterized in terms of this bit error rate. So bit error rate is kind of, so how do you classify whether two instances are different? So you use fractional Hamming distance. So here also we calculate the fractional Hamming distance between the response bits corresponding to two different measurement instances or different operating conditions. And then we divide it with the total number of bits in that response stream. So that kind of gives you the number of errors, number of bits which have error divided by the total number of bits. And that gives you kind of bit error rate. So the problem with this kind of simulation-based approach was that Monte Carlo simulations do not depend on time. If you perform Monte Carlo simulations now, and if you perform the same simulation 10 years down the line, they'll give you the same results. There is no change in time. So with the help of Monte Carlo simulations, you cannot capture this time effect. So we could not perform that analysis even though we wanted to. For that, we needed experimental data that we didn't have. So instead, what we did was we just characterized, the impact of varying temperature and fluctuation in the bit line voltage independent of time. And that is because we didn't have experimental data on lift, stress, and all those things. And what we found was that the bit error rate was also fairly small. I mean, for a temperature of 125 degrees Celsius, the bit error rate was close to 5%. And for change in the bit line voltage, even if it goes to even if it goes to, from 0.8 to 0.4 or 0.6, you see that the mu or the fraction Hamming distance is pretty small. The bit error rate is very small. So this is also very reliable. I mean, the 3D NAND flash PUF that we proposed was also very reliable. So yeah, these are some numbers that it was 4.26 at 125 degrees Celsius and 1.13% for a fluctuation by 0.3 volts. So that is perfectly fine. I mean, these are very less numbers. I mean, they are kind of good numbers in terms of reliability characteristics. Now let us talk about the machine learning modeling attack that I have been discussing so far. So as I told, what we can do is we can use a machine learning model, let us say a multi-layer perceptron, or we can use any SVM, we can use KNNs, we can use all sorts of machine learning models, CNNs, RNNs, kind of get an information about the response bits that we'll get from unknown challenges. So what I did was, for applying this machine learning modeling attack, I started thinking like an attacker. I started thinking that I am the adversary, which is going to attack on my PUF. And then what I did was I generated this 48 cross 500 cross 500 cross 1 kind of multi-layer perceptron to test my PUF design against the machine learning modeling attacks. So what I assumed was, since I am the adversary, since I have access to that channel through which we will communicate the raw challenge response pairs, I will have access to a limited amount of CRPs. Since the number of CRP is huge here, why the number of CRP is huge? Because the number of such bit strings is large. So in a NAND flash array, you already know that the page size is 1024, you have 116,384 such strings in each page. So the overall kind of number of CRPs that you can generate using this 3D NAND PUF is quite huge. It's in the range of 10 power 55 or something. So that is huge. And that is why in limited time with limited amount of resources, anyone can't, extract these 10 power 55 challenge response pairs. What you can probe in, let's say, a timeline of 1 year is some million challenge response pairs. So what I assumed that as an adversary, I could access those challenge and response pairs, but I could access only a limited portion of it. Let's say some million, 10 lakhs, or let's say 20 lakhs. So I went till 50 lakh samples, which is kind of a reasonable number, which you can do within 2 years of time. I mean, reasonable number of CRPs, which you can probe within 2 years of time. That is what I did. And the challenge here is, I mean, the question that I posed to myself was, given the known CRP set, can we predict the response bits of an unknown challenge? That was the kind of problem at hand, and I had to train my neural network to do that. So what is the challenge? As I told, it's 14-bit bitline address concatenated with 10-bit word line address. So we have 24 of this corresponding to one string and 24 corresponding to the other string, for which we have to compare the current. So the total input bits was 48, and that becomes, the input which I have fed to my neural network. And then for a particular word line address, a subset of the total CRPs was chosen as a training set. So the number of CRPs that I have, I'll use it to train my perceptron, and then I'll use it to test on an unknown challenge and see whether the response that I'm getting via my neural network model and what I get from my circuit are same or not. So this was what we found. So the accuracy on training set was huge because my model was able to, since it's a huge model, it's a 48 cross 500 cross 500 model. It was able to, and why is the output 1? Because I only am interested in knowing whether the response is 0 or 1. So only one neuron can tell you that. So accuracy on training set was huge. Why? Because if the training set size was small, when it was 10 power 4, 10 power 5, 10 power 6, my network, since its size is huge, each of the neurons could, remember or learn all these training set. So the accuracy on training set is high when your training set size is small. As your training set size increases, accuracy on even training set reduces because now your network cannot remember each and every CRP set. However, if you look at the accuracy on the test set, it has always given an accuracy of 50%. What does that mean? 50% accuracy simply means that it was not able to predict correctly whether it is 0 or it is 1. So when is your accuracy 50%? When you're not able to decide, right, whether it is a perfect 0 or a perfect 1. So this near ideal unpredictability, that is 50% accuracy on the test set, it's not training set, it should be test set. It simply indicates that this 3D NAND PUF are also, resilient to machine learning modeling attacks. And this was one of the kind of, I would say, achievement of this kind of study. So with this, I would end this lecture. And in the next lecture, I would discuss about, PUFs, not PUFs, RNGs.